Hello and welcome back to another lesson in pre-calculus. This is our last lesson on polynomials for this unit. This is Mr. Bean, and the first thing I want to point out is we are not going to use graphing calculators in this lesson. Okay, important thing here, you've got to know how to do this without. And some students are going to be like, whoa, just let me use a calculator to do this, please. But the reality is many of you are going to be going on to calculus, and if you take the AP version of calculus, then the AP exam, half of it, actually a little bit more than half, you cannot use a calculator on. So we've got to have some of our lessons here where we're practicing some things without calculators. So just be aware of that. Same thing on the mastery check. So let's first talk about some general things you can say about polynomial graphs. First of all, there will be no discontinuities. Okay, these things are just going to go on forever and ever, and there's never any holes or gaps or anything like that. There's also no sharp corners, so you don't have any of these things like absolute value graphs where you have corners on them, nothing like that. So nice soft curves, and then all real numbers for your domain. Goes forever to the left and forever to the right. Okay, so quick little things about polynomial graphs. So now you've already actually seen a lot of these. In the past, for years, you've been doing linear functions. That's a polynomial graph. Quadratics, where you have some type of parabola, that is a polynomial graph. We've been doing those. Cubics, you've seen some of that stuff. It might turn around and have some turning points in it, or it might not. Kind of depends on the particular graph, but that would be an example of cubic. And then quartic, where it might have a couple of turns in there. It may not, but that's a possibility for quartic. Those are graphs you want to be able to know the names of for sure. Beyond that, the names of them, that's not going to be that important for us. Now, the end behavior. When we say end behavior, we're talking about what the left side and the right side's doing. So if the leading coefficient is positive and the degree is even, I want you to think about what that means. That is something similar to an x squared graph. If the degree is even here with a 2, and then the leading coefficient is positive, it's just like an x squared. So in other words, it's going to have something that's going like this. Now there might be some squibbles and some turns and stuff going on in the middle, but it is doing something like this, where the left side goes up and the right side goes up. And then if we had a negative, so in other words, if this was like a negative x squared right here, this one, then it would be sort of like a parabola, but a blue might have some weird stuff going on in the middle and then going down. Now, I don't really care what's happening in the middle, because that just, all I'm talking about is the end behavior, the left side and the right side. So I always think of this as just like a parabola, and then if it's positive, look at this, positive people are happy, and if it's negative people, they're just like a bummer to be around. Negative, always upset. See how you do that? So now how do we plug this in? Limit. As x approaches negative infinity, this is the left side, and so the graph's going up. So you throw in your positive infinity, and the right side's going up as well. And on this one, both sides are going down, so it's negative infinity on both of them. That's how we talk about the end behavior. Now let's do odd. I think of odd, you could think of it as a line. I'll usually tend to think of it as kind of like a cubic. And so if you have a cubic like this, in fact, what I should do is put a bunch of squiggles in the middle. And so because it might, we don't know for sure if it's exactly a cubic, but it might be doing something else like that. Again, middle does not matter. And then if it's negative in front, so this is when it's positive, and I always think of the slope's going up, left to right, just like a line would be going up with positive slope. Well, if it was negative slope, then the thing would be going down with some squiggles in the middle. That's negative slope, or like this, a line going down. So leading coefficient's negative. So what do we have here? The left side is going down, and the right side's going up. And then on this one, the right side is going up, so it's positive infinity, and the right side is going down, so we put negative infinity. Oops, there we go. All right, there's your end behavior. In a nutshell, using limit notation, the big thing here is making sure that you know how to kind of draw a quick little sketch to have an idea of what's going on, so that then you can come up with the end behavior with limit notation. Now on to turning points, zeros, and multiplicity. This will be a new one here when we get to it. Turning points. Turning points is like the extrema that we talked about. How many turning points are in it? Well, if you look at the degree n, then it's going to have at most n minus 1 turning points. Let me use an example. X squared. How many turning points does that have? A parabola will turn around one time. 2 minus 1. The degree is 2. So it has at least one turning point. Or a cubic could have, a cubic is x cubed, x to the third, and so it has one less than that turning points at most. So 1, 2. Now, it might not have any. For example, this is another cubic graph like that, and there is no turning points on that. It doesn't actually turn around. So it's possible it has less, but it will have at most n minus 1. And then the zeros, or the roots, same thing, zeros and roots, it has at most whatever n is. So we learned this in the last lesson with the fundamental theorem of algebra, where we look at the, I should say real zeros, at most n real zeros would actually be a better way to put that. In fact, let's add that in. Add that to your notes. We're talking about real zeros here. So if I say x squared, we're talking about where it crosses the x-axis. So if I have a graph here, it could cross 2 times. It might touch it only once, like if I had a parabola that came down and just barely touched it like this, or it might not cross it at all. Like if I have a parabola that kind of opens down like this, and it never even touches it. So at most n can't cross more than n times, whatever your degree is. And then lastly, multiplicity. Multiplicity is basically how many times the factor is showing up inside the function. So once you factor the whole thing, the multiplicity is, for this one, this factor showing up 2 times, so its multiplicity is 2. This factor, x minus 3, is showing up only 1 time, so we say that x minus 3 has a multiplicity of 1. Or another way of saying this is that the 0, x equals 3, that has a multiplicity of 1 as well, the 0. And so this 0, x equals 7, has a multiplicity of 8 because it's showing up 8 times in the factor. Okay, not too difficult of an idea, but it is important for something that we'll do with the graphs. You have to examine the multiplicity. So this is what the graph is going to do with multiplicity, even or odd multiplicity. Let me draw a quick little Cartesian plane, and with this we'll say out here is about where x equals 7. We'll say that one's x equals 7. And multiplicity being even means that the graph, I don't know what this graph is doing, something like this, but when it comes down here to x equals 7, it is tangent right here. Okay, or another word of saying that is that it kisses the graph. Ooh, that was sloppy. Kisses. Okay, so kissing or tangent, that's the same type of thing. So it is not going to cross it. It's either going to stay on the same side, either where that's the positive side or the negative side. That's what the tangent does for our 0. What about for this one? If it is odd multiplicity, so on this one, x minus 3 has an exponent of 1, that means it is crossing. So let's draw another quick little Cartesian coordinate point system here, and we'll go over here to where x equals 3, 1, 2, 3, somewhere about there. And graph is crossing it. Whatever it's doing over here, I don't know, but definitely right there it is going across it. That's going to help us quite a bit when we try to sketch just the general shape of our graphs once we know the zeros. You also look at the multiplicity. So let's do an example. Number 1. We have all of these things here. So how does the graph behave with relation to the x-axis at x equals 2? So here's our x-axis. At x equals 2, we are talking about this factor right there. Since the multiplicity is even, it is going to be tangent to the x-axis, or in other words, it kisses it. Just kind of comes down to the 2 right here. But I'm going to put my zeros. Oh, that's actually the next point here. B. What are the real zeros? So let's list them. We have -1, and we have a 2, and we have a 1. Don't include this one because it's just a number. There's no variable there, so we don't need to worry about it. Some students like to put a 0 is the other 0, but that's not true. There has to be a variable there for that to be a 0. All right, plot these little zeros. We have a -1, a 2, and then a +1. What is the degree? The degree of this function, be careful here, this is an x, this is an x that's being squared, this is an x that's raised to the 3rd power. So when you multiply these all out, you basically have x times x squared times x cubed for a total of x to the 3, 4, 5, 6th power. So the degree is 6. Okay, see how I do that? You're going to end up multiplying. You don't care about all the rest of the stuff that you multiply out. You are only caring about the very first term. So 6 is the degree. So let's describe the end behavior. First, let's do the left side. So the limit as x approaches -infinity of f of x is going to equal. What's the left side doing? Well, I know, I'm going to come underneath here, I know that if it's even and the front is negative, it's unhappy. It's doing something like this. Okay, it's going down on both sides. I know that. So that will help me know that both sides are approaching negative infinity. And then I'll do the right side, the limit as x approaches infinity of f of x. That is going to equal also negative infinity. Okay, now we sketch a graph, and that's it. So we know that on this side it's going to be going down like this, and on this side it's also going to be going down, something like this. And the rest of this, we do not need to be accurate with hardly any other points. Okay, really, we're just sketching a basic understanding of what the graph looks like. The big thing here is that on my first 0, -1, it is going to be crossing. X equals 1. Let's do that one next. 1. At x equals 1, 0, that one is crossing as well. So that one's got to be, when it goes up, it's got to be coming back down. And then on this one, x equals 2, this one has an even multiplicity, so it is tangent right there. So now here, the rest of this stuff, we just fill it in. So now how high up do you go? This is just a sketch. It doesn't really matter. We don't need to be accurate on the y-intercept. We're just kind of sketching this thing like so. What we'll look at for grading purposes is your end behavior correct? Do you have, whether it's tangent or crossing, does it all fit together and work out for you? Okay, before we go to example number 2, let's watch a quick little cartoon. This has to do with multiplicity in a way, because multiplicity means there's multiple things of something. So I found a little cartoon clip of some clones.
Come on, man, give it up. You're overpowered. Hold on, guys, think about it. We're exact equals mentally and physically. If we start fighting, it'll just go on for infinity. It's true when you think about it. Just give up. Clone fight! Hey, you! Quit hitting myself! Quit hitting myself! Guys, come on, it's me! Hey, you! Me! Hey, Classic Dipper's getting away! No, friends. It's me, number 7. That's not me, guys. That's not me! Get him! Stay back. Stay back. Yeah. Boo! Lame! Huh. How about that? You! Uh-oh.
Okay, I hope you enjoyed that. You know, I don't even know the name of that cartoon. My kids watch it. It's actually kind of annoying to me, but I guess they love it. Number 2, factor the function blah, 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 and sketch the graph if f of -2 equals 0. This right here, right away, that's telling me that I have a xy coordinate point, -2, 0. So I'm going to go over here, -2, 0, and I'm putting a point before I do anything else, just to remind myself that is a coordinate point. Now, what else can I do with this? If I got to factor this thing, this is where you need to use the skills we learned in our last lesson, which is factor the whole thing. Well, I know that x plus 2 is a factor. So let's see. I've got a leading coefficient of 1, 6, -8, -96, -128, and 0. Right? Yes. Okay, this whole thing here, 5, 4, 3, 2, 1, and then I had no constant term, so I'm going to put a 0 there. All right, let's factor this down. I put nothing there, so a 1 comes down. In fact, yeah. -2, 4, -8, -16. Multiply by -2, I get a -32. Add together here. That is, I made a mistake. What happened? Oh, there, -16, lost that. So that makes this positive 32. Put those together, you get 64, that's -64, times -2 is positive 128, 0, 0, 0. All right, now we bring this down a level. So it was x to the 5th, we now have x to the 4th, plus 4x cubed, minus 16x squared, minus 64, and then 0, 0. So this, 64x. All right, so now let's factor this.
Let's factor out an x. You get x cubed plus 4x squared minus 16x minus 64. And then I'm also going to tag on here x plus 2, because I know that this -2 being a 0 makes this a factor.
Okay, why don't you pause the video here. I'm going to have the rest of the factors appear. Just factor this thing. You're going to use factor by grouping for this step. there should have been a difference of squares with x squared minus 16 that you get. So now we have, and this is important to recognize, we have two x plus 4s. There's one there and one there. So that one is repeating, which means the multiplicity is a 2. Let's go back to our graph and start graphing these. We have x equaling 0. That will be 1 because each factor is going to represent a 0. We have x equals negative 4. It's showing up twice, but we got to go out here to negative 4. We have x equals 4 being another 0. 1, 2, 3, 4. And then we have the one we already graphed, which is x equals negative 2. So what's the end behavior of this? It's odd, and the leading coefficient is positive. So if it's odd and leading coefficient is positive, it's going up as you move left to right. So it's going down here and going up here. So that's the first thing I'll do. And now we just need to start plugging in what is happening with each of these zeros. Let's start with the first one here on the left, negative 4. This one is showing up twice, so it is tangent. Its multiplicity is even. This, and then the rest of them are all odd, so it's crossing. So it's going to cross here, it's going to cross here, it's going to cross here, and that makes sense. Now you can kind of piece it together, and that'll all make sense the way that the graph is supposed to look. Again, this is not exactly accurate because I don't know what these y values are. It could be way up top, way down low. We're not using a calculator, so they don't have to be accurate on this. We're just trying to get a general shape of what the graph is doing. Okay, number 3. This one should be pretty quick and easy for you. I'm giving you a graph. Let's find the local min, max, minimum degree, that stuff. What's minimum values? Minimum values, local min values, are going to be y values. So don't forget that. These are all y values. That's what we're talking about. And what is that? 1, 2, 3, 4. So we have negative 4. And what's this one? Minimum value of negative 2. Local max, here and here. So there's the same one, so we don't have to list it twice. We just put 0. We don't need to say 0, 0. It's the same thing. So local maximum values of 0. Remember, it's y values. Okay, now minimum degree. I know it has to be odd. Okay, that's one thing. I know that it's odd, but what is the actual smallest amount it could be? Well, let's see here. It has 1, 2, 3, 4 turns in it. If there are 4 turns, if you come back to our notes where we said that it's going to have at most n minus 1 turns, and if it has 4 turns in it, that means the minimum degree is going to have to be 5. It's kind of like working backwards from that. So minimum degree on this one is 5. Because if the minimum degree was 3, then it would only have 2 turns in it at most. This one has 4. So let's write a possible function, and then we don't need to multiply it out. Let's just write out. So f of x equals, the thing is positive because it's going up left to right, so we'll have a positive in front. And let's just list these left to right. Here we have 1, 2, 3, 4, 5, 6. So let's say x plus 6. That makes a negative 6 is 0. And then its multiplicity is even, so we could just say squared. As long as it's even, then that's good. You could technically put any even number there. Okay, next one. Here's another 0. At x equals 0. That one is also even, so I'll put an x squared. And then times, what's my next one? Right here. 1, 2, 3, 4, 5. So at x minus 5, and that's crossing, so it's odd. I could put a 1, we'll leave it 1, 3, 5, anything like that. There you go. That's simple. Done. You do not need to multiply this out. We're just setting up a basic function. Now, there could be a coefficient here. You could also put any number in front that is positive, but not necessary. We're just trying to get a general idea of what one possible function could be. Okay, we're last thing of our notes, and then we're finishing up. This guy, French guy, is called Descartes, René Descartes, something like this. René Descartes. I don't really know how to speak French, but I asked our French teacher. That's what she said, how you pronounce it, Descartes. This rule is actually pretty cool. It is talking about the number of positive real zeros and the number of negative real zeros. I'll come back to this in a second, but what's cool is I want to talk about this guy because he lived a long time ago, 1600s. He's a philosopher, a writer, and a mathematician. This is so cool to me because, you know, we don't think of mathematicians as being these philosophers and writers and things like that, but back in the old days, they were pretty cool. He's the one that you've ever heard of this phrase, I think, therefore I am. He's the one who came up with that. Philosophical circles, they rely on him a lot. He's also where we get this thing called the Cartesian coordinate system. In fact, I've even used that word in this lesson. When you have a coordinate plane, it's the Cartesian coordinate plane. He came up with it. It's the reason it's Cartesian is because when you when you do the Latin version of it, it's like Cartesium or something like that. That's why it's Cartesian. And he's the father of analytic geometry, which the main reason that's big says we rely on this for the foundations of leading into calculus. So I guess you could maybe say he's like a grandpa of calculus. And then he's basically a genius. They consider him a pretty darn smart guy. So what is this thing up here? This positive real zeros, negative real zeros? Well, what he figured out was that when you have a coordinate system and you have this polynomial and stuff that's going on, the number of times it's going to be over here on the positive side versus the negative side. So the negative side versus the positive side of your y-axis for the x-axis has to do with the number of changes in sign. Okay, so let's get this written down and I'll show you an example how this works. If it changes sign, the number of times it changes sign of f of x, that's how many positive real zeros there could be. The number of times it changes sign on the left side on the x-axis depends on the changes of sign of f of negative x, or less than this by an even number. Get this written down and let's do an example.
So here's how you do this. You first take, we're going to try and figure out how many positive zeros might there be. In other words, remember how many times this graph might be crossing the x-axis on the positive side of the y-axis. So what we do is we look how many times the sign changes. Now the first thing is make sure that each term is counting down in order. So this is the 6th power, the 5th power, x to the 4th power, x to the 2nd. It's okay that we skipped x cubed. It doesn't matter if we skip things as long as they continually decrease down until you get to just a constant. All right, now what we'll do is we're going to look for when a sign changes. This is positive, this is negative. So that right there is one sign change. This term is negative, this term is positive, there is another sign change. And then the next one is negative, so there's another sign change. Again, it's okay that we skipped x cubed because there's a 0 in front of x cubed, so it doesn't really have a sign, so we just ignore that one, so get rid of that. It's okay that we skipped it. Oh, that was off my screen, sorry, when I was drawing. And then what's next? That's a negative sign. This one is a negative sign, so there is no sign change there. We don't worry about that one. And then this is a negative and this is a negative, so again, there is no sign change. So how many times does the sign change in this? 3 times. So our answer to this, how many possible number the possible number of positive zeros, that's a tongue twister. So that is 3. Now that's the maximum number of zeros there could be, 3. But if we go back here and we see what is the number of sign changes, it's going to be that number or less than that by an even number. In other words, if that number is our n, then there could also be n minus 2. And then there could also be n minus 4, if I squeeze that in. So this is there's 3, or there could be 1, or that's it. There's no other number. Because if we subtract 2 more, if we're at 3, we subtract 2, we get 1. Subtract 2 again, we'd be at negative 1, and so that's a negative number. We're not worrying about that. So there's either 3 or 1 times that this graph is going to cross the x-axis on the positive side. So it's kind of cool. It helps us narrow down where our zeros are. All right, so now the negative. This one's a little bit trickier. Here's how we do the negative. We're going to plug in a negative x into the function. So we actually have to write this out. So if we plug in a negative x, we're going to end up with 2x to the 6th. Now why? Because if I plug in a negative x to the 6th power, an even power is going to make it positive. So basically, as I look across here, the even powers, 6, 4, and 2, are going to keep the same sign. It doesn't change. But the negative ones, so this next example, the negative one is going to, instead of it being minus 3x to the 5th, it now is going to change. Why? Because negative x to the 5th power is going to equal negative x to the 5th, like that. So that makes this now a positive. So it just changes the signs if you have an odd exponent there, an odd power. So then this one is even, so it stays the same, plus 7x to the 4th. This one is even, so it stays the same, so minus x squared. This is to the 1st power, right? So it changes, so that's no longer a minus. It's going to be a plus 2x. And then minus 11, nothing changes there. Okay, so now let's count how many times the sign changes. Positive to positive is nothing. Nothing changes there. Positive to positive, nothing changes there. Positive to negative, there we go. There's 1. That changes. Negative to positive, the sign changed. And then positive to negative, the sign changed. So how many negative zeros might there be? In other words, how many times might it cross the x-axis on the left side of the y-axis? 1, 2, 3. 3 is the maximum times number of zeros that it might have over here. And then we subtract 2, and there could be 1. Subtract 2 again, we'd get to negative, so we don't have to deal with that. If it went down to 0, like if you had 4 possible zeros, you would then do 2, and then you would do 0. So that would be the answer. But this one is just 3 and 1. This one is also 3 and 1. Now, what I'm not covering in this lesson is that there's also this thing called imaginary roots. And so you would be able to know, since the term here is 6, it would have to add up to 6 zeros. So if I had 3 positive and 3 negative, then that's a total of 6. If I had 3 positive and 1 negative, then there would be 2 imaginary zeros. So we're not going to have that in that lesson, but I just wanted to at least throw that out there at you, that you know there are these things as imaginary zeros as well. Okay, this is Mr. Bean signing off. Rock that mastery check, and I will see you back. I'm not going to see you back until next semester. Holy cow, I don't think I've come back until Unit 10. All right, we'll see you.